Mats has done so much, so it's impossible to cover all aspects. I will be able to cover only some aspects. So first, a short CV. He was born in Gothenburg and grew up in Gothenburg, and then he studied chemical engineering at the Chalmers Technical University in Gothenburg. And after his degree, he went up to Stockholm and started as a researcher at the Swedish Institute for Metals Research. And 1953, he started studies in physical metallurgy at MIT. And it was Maurice Cohen who was his supervisor, but he learned thermodynamics from Carl Wagner. And he got his doctor's degree from MIT in 1956, and then he started to teach at KTH, and he was appointed full professor in physical metallurgy at KTH and he 1961, and he was active for 30 years until he became professor emeritus. But after that, he was active for more than 30 years until his last day, I would say. Well, there are two major fields where he were active, phase transformations and thermodynamics. But they are quite interwoven, and many reports contain both of them. And his research record is so extensive, and each publication is quite unique. You know, many people write the same publication many times, but Mats didn't do that. They are quite unique. So here is what I would like to cover today. First, phase transformations, the local state of migrating interfaces, which is a subject that Mats came back to many times during his professional life. Solid drag and massive transformation, the spinodal decomposition, diffusional transformations, grain growth, discontinuous precipitation and DIGM, martensitic transformation, and then thermodynamics, the early vision and the compound energy formalism, the magnetic effect, and also the international leadership in this area, the CALPHAD community and STT. And I will end with a book and some educational material. So here is a young Mats studying phase transformations, I believe. So he often used the local equilibrium hypothesis to predict the rate of phase transformations. In that method, you assume that the two phases on each side of a migrating phase interface are locally in equilibrium, and then the rate is controlled by diffusion from and to the interface. Now, this is a very powerful method because it only needs bulk properties which can be measured independently. You don't need to know anything about the phase interface. And moreover, the results are often in satisfactory agreement with experimental data. When you apply this to steels, carbon diffuses many, many orders of magnitude faster than the substitutional elements. And that means that the method predicts two quite different cases, either a very slow reaction controlled by substitutional diffusion, or a quite fast reaction controlled by carbon diffusion. So if you look at the fast reaction, here I have a schematic concentration profile for a substitutional alloy element. And since there is no redistribution or very small redistribution of the alloying element, the growing alpha phase in this case inherits more or less the composition of the gamma phase. But in order to have the local equilibrium, and that is illustrated here by a Turner section, and this is from an early paper by Mats, there needs to be a spike in concentration, in substitutional concentration, pushed ahead of the interface. Mats estimated the thickness of that spike, and it turns out to be the diffusion coefficient of the substitution element divided by the velocity of the interface. Now, if this is much smaller than atomic dimensions, Matz argued that it could have no physical meaning. And he called this true par equilibrium, or later simply par equilibrium. Par equilibrium, and this is discussed now in a report, internal report from 1953. The par equilibrium as a concept was introduced by Hillert some years earlier, and he defined it as a case where the growing phase had the same alloy content as the parent phase, but different carbon content. So it was not a very precise definition. But Matz's definition is precise. It is a true thermodynamic equilibrium, but it is a constraint equilibrium. So it's full thermodynamic equilibrium for carbon. But this Turner system, ion, an alloy element M, and carbon, it behaves like a binary system, X carbon, where X has the weighted average properties of ion M. Oh, no, I can't switch. Then I go to here. Oh, I seem to have some problem. Yeah, okay. On the other hand, if the thickness of the spike is larger or sufficiently larger than the atomic dimensions, it would have a physical meaning. And this was called false par equilibrium by Matz. And nowadays we usually call it negligible partitioning local equilibrium, or NPLE, which was introduced by Coates 1972. So how does the transition between NPLE and par equilibrium occur? This was something that Matz discussed many times. And in an internal report, 1960, growth of ferrite, bainite, and martensite, he analyzes his own experimental data and experimental data from other researchers. And he managed to evaluate the deviation from local equilibrium. That is in the gray zone between NPLE and par equilibrium. And he suggests a mathematical representation for that deviation. And then he could use it to calculate the edgewise growth of a plate, for example, a ferrite plate. So here is his results. And on this axis, we have the curvature. So it's the inverted radius of curvature. And here we have the velocity of the edge. And each curve here is for a certain supersaturation. And at very flat interfaces, and you start to sharpen the interface or the edge, then it goes faster due to the diffusion effect. But at some point, the effect of the curved interface and interfacial energy sets in, and the rate goes down again. And then we connect all the maxima for the different supersaturations with this dashed curve, because Matz applied Zener's maximum growth rate principle, which says that we would observe in nature the radii which have the fastest growth rate. But then you see here at some point, there is a critical point. And for supersaturations larger than that point, there is only one continuous curve. So Matz interpreted this as a case, if you are beyond that, you will get transition to a very fast reaction, which is essentially diffusionless. So I'll come back to this. Now, par equilibrium and Nple, they are thermodynamic extremes. And they have had a very large impact on steel science. And both those extremes, they allow you to calculate the rate of a phase transformation without knowing the details of the phase interface. And here is a citation from Brecher and Philibert in the selected works of Mats Hillert a number of years ago. One can safely say that this paper has been one of the most influential unpublished papers of physical metallurgy. Solid drag and massive transformation. Now, if you have a grain boundary, impurities may segregate to the grain boundary. And if there is a driving force, for example, during recrystallization, the grain boundary will move. But in order to stay in the grain boundary, those impurities have to diffuse inside the boundary with the moving boundary. And Mats, he realized that this diffusion process would need some of the driving force available. And then the motion of the grain boundary would be slower. So the boundary drags the impurity atoms. And moreover, when the driving force exceeds the critical limit, there is a transition and the grain boundary motion becomes diffusionless, which means that the impurities, they are simply left behind. And then the grain boundary can move with a high velocity. So there is a sense, in a sense, there is a similarity with the diffusionless phase transformation. And that was, of course, realized by Mats. So Mats and Bo Sundman in 1976, they formulated a thermodynamic model for a grain boundary and combined it with a steady state diffusion equation. And then they could calculate the concentration profile in a grain boundary for different rates of migration of the grain boundary. Here is one example. So you have a stationary grain boundary, curve number 1, and then curve number 2 and curve number 3 are for higher growth rates. And you can see that the concentration profile is pushed down the higher, the faster the grain boundary moves. Now, if you look at the transition to a diffusionless phase transformation, if you start with an alpha phase here and cool down into the alpha beta 2 phase feed, there is a T0 line, which is the thermodynamic limit because below which a diffusionless reaction is possible. It is defined as temperature where the two phases, alpha and beta, have the same Gibbs energy for the same composition. And approximately it falls in the middle of the two-phase field. So if you don't know anything, you can tentatively put it there. And then a year later, Mats and Bo, they applied the same approach for solidification. And now they assume linear variation in thermodynamic properties across the solid-liquid phase interface. And they considered dendritic solidification and accounted for the interfacial energy at the growing tip. And this is the result they obtained. And you see, this is very similar to much simpler treatment from 1960. So you have the curvature down here and velocity here. And then those curves are for different supersaturations. And again, there is a critical point. So when the supersaturation becomes bigger than that, the reaction turns diffusionless and goes very fast. And that information is here, which is for one temperature, is here transferred to the binary phase diagram. And the solid line here is a T0 line, and the dashed line here is the critical points. So when you cool below that point, that dashed line, there will be a spontaneous change to diffusionless solidification. So we can look at this also in the solid state. In the solid state, we have what is called the massive transformation. It is diffusionless, and it occurs by migration of an essentially incoherent interface. So it is different from the martensitic transformation, which we will come back to. And Mats and Annika Borenstam in year 2000, they used a gradient technique to study experimentally the massive transformation from austenite to ferrite in iron nickel. And the symbols here are their experimental results. And you can see, of course, they fall below the T0 line. Otherwise, it would be impossible. But they also fall in the two-phase field because there were many discussions at that time if it could fall into the two-phase field. And those dashed curves are calculated using different assumptions about the properties of the phase interface. Now, you may realize, at least Mats did it, that growth under par equilibrium conditions may be regarded as a massive reaction with respect to the substitutional alloy elements and full local equilibrium for carbon. So it could be modeled with similar approaches. And here's one example from 2002, together with Joachim Oldqvist and John Ågren. And it shows gamma alpha two-phase field at 700 degrees in iron nickel carbon. And here is a gamma part of the phase diagram. And this solid line for a given alloy, the alloy content is given by this dotted line. This solid line now represents different possible states of the migrating interface. So here you start with something close to Nple, and down here you have full para equilibrium. So you see this growing phase now has the same composition as the alloy, whereas here you have the spike. Now we come to a rather different subject, spinodal decomposition, which turns out to be a competition in science. As a background, the classical nucleation theory is from Vollmer and Weber, 1926, and that was later improved by many authors, and it is what is used still today. But it is based on the concept of a critical size, and it only holds in stable or metastable solutions. In the middle of the last century, there was intensive discussion what would happen with nucleation if you were inside a miscibility gap, and particularly inside the spinodal, which I will come back to, because inside the spinodal, the material is truly unstable. So the classical theory does not hold. And that was the subject of Mats' MIT thesis from 1956, a theory of nucleation for solid metallic solutions. So if you have a binary phase diagram, the spinodal curve is determined by the location where the second derivative is 0. So here is a part of the phase diagram with a miscibility gap, and here is a spinodal. And you can see for the Gibbs energy curve, at this temperature, you have the spinodal curve at the inflection points of this Gibbs energy curve. So in his theory, Mats considered variation in composition rather than size. and he used a nearest neighbor interaction model, a one-dimensional model, to describe the Gibbs energy. And so the Gibbs energy here was a sum over all atomic planes, and each plane is has a composition given by an X. And then he could schematically plot the Gibbs energy as a function of wavelength and amplitude when he considered periodic variation in composition. And if we look at this side, we have a composition in the middle of the miscibility gap, and that is in the middle of the spinodal. Then it turns out that below this point, if you increase the amplitude, it will just go up. But then there is a critical point here where you get a minimum, and you can see it here as a valley. So from this critical nuclei can now move down in this valley and have a continuous decrease in Gibbs energy. And this is outside the, well, it's inside the spinodal, but not in the middle. And now you can see that there is a barrier here which you have to pass before you come down to this valley. So these are maximum points, and those are minimum points. And here there are only minima. Now, Mats had to look at extremum conditions by solving difference equations, which was tedious. Darken's equation showed that the diffusivity inside the spinodal would turn negative and lead to uphill diffusion. And then Mats realized that the diffusion equation needed to be revised. And based on his neighbor approximation, nearest neighbor approximation, he actually derived such an equation. And it contains an extra term compared to the conventional equation. But unfortunately, when Mats was at MIT, the computer facilities were rudimentary, and he could not solve the equation. Kahn and Hillert, 1958. Well, John Hillert shared office with Mats, and he showed a copy of Mats' thesis to John Kahn when they met at General Electric's 1956. And they became inspired by his work, and they developed a mathematical representation based on continuous functions rather than difference equations. And one may say that they thus completed the theory, but they referred to Mats, and in their acknowledgement they said, "We also wish to thank Mats Hillert of the Metallographic Institute at Stockholm, Sweden, for providing us with a copy of his thesis, which initiated our interest in this subject." So what about the diffusion equation? Well, Kahn and Hillert, they never formulated any diffusion equation. It was presented later, actually only by Kahn, but it is called the Kahn-Hillert equation. So when Mats came back to Sweden, he got access to computers, and he could solve his diffusion equation. And here is the diffusion equation, and here is typical result. And he published his paper in 1961, but it was actually submitted half a year before Kahn submitted his paper. And Kahn mentions that he had access to Mats' manuscript before Kahn's paper were published. Diffusion transformations and effect of pressure and interfacial energy. Already in a talk 1953 at the Swedish Metallographers Association, Mats discussed the effect of pressure on diffusion. But the full paper had to wait until 1957. Now he assumed that the diffusional flux is proportional to the gradient in activity. And he realized that this was equivalent with the flux proportional to the gradient in chemical potential, which is what we use now. And he evaluated the effect of pressure on the activity from this well-known thermodynamic relation, and that gave rise to pressure-induced diffusion. So he applied that to graphite formation in steels. Here is one of his curves. So here is a logarithm of the square of the size of a graphite sphere. And here is a logarithm of the growth rate of this square. And here he looked at different mechanisms, and those are for 3 different alloys. In another paper the same year, Mats showed that it is straightforward to include also the effect of interfacial energy in the local equilibrium approach. He started with the effect of an isotropic interfacial energy, which causes a pressure difference between the 2 sides of a phase interface. And here is isotropic interfacial energy, and those are R1 and R2 are the radii, principal radii of curvature. And of course, by multiplying with a molar volume, you get this into a driving force. This was used in his theory of perlite growth. So Mats, he represented the carbon concentration field in austenite ahead of the perlite front with a Fourier expansion with a periodicity S, which is interlamellar spacing. And this is actually an exact solution to the 2-dimensional diffusion problem if the carbon diffusivity is constant and you expand then the concentration in a kind of series like this. And he combined that with the mass balance and the effect of the interfacial energies and sinus maximum growth rate principle. And then he could solve the problem. And after solving the problem, he could then calculate the shape of the interface. And this is a shape for a different lamellar spacing. And this is in, well, reasonable agreement with micrographs. But he also studied the perlite growth experimentally. So in a paper from 1961, he discusses the details of metallographic observations and from his own result and from other researchers. But the remarkable thing is Mats and Nils Lange, they made an extensive study by serial sectioning of a single perlite colony. It was cut 242 times, and then they transferred all those micrographs to a movie. But of course, you cannot publish a movie. So those really remarkable results were never published, at least not at that time. It had to wait until the modern computer technology allowed the proper representation of the extensive data. And this was published by De Graaf and Kral in 2006. And here is one of their micrographs showing the cementite lamella of a perlite colony. And of course, then you can turn this in order to look at the structure. In a paper from 1964, Mats uses a common assumption that the velocity of a grain boundary is a mobility times the driving force on the grain boundary. And this driving force comes from the pressure difference by the energy and the curvature of the grain boundary. So then he considered an assembly of different grains, and he applied a mean field approach and postulated an expression for all grains with an average size between R and R plus dr. And it looks like this. So alpha is a numerical constant, approximated as unity, mobility, and grain boundary energy. And this is size, grain size in this size class. And this is the critical size. So grains which are smaller would then shrink, and grains which are bigger would grow. And then, of course, you need to see how could this be transformed into an equation for the average grain size. How does that develop in time? And then he used the same procedure as Lifshitz and Slosov used a couple of years earlier when they analyzed Oswald ripening. And he found that the average size were proportional to the critical size, and he found a differential equation which was easy to integrate, so you could calculate how the critical size depends on time. And so approximately this gives a critical average time which is proportional to the time raised to 0.5. And that is in agreement with the experiments. But he could also calculate the size distribution, the grain size distribution, and that does not agree well with experimental data because it is skewed towards the larger sizes, whereas experimental data is skewed in the other direction towards the smaller sizes. Then he also discussed the secondary particle pinning and the tendency to abnormal grain growth. Discontinuous precipitation and DIGM. This is a picture from A.C. Shao and Notice from a copper alloy. Well, this is not a eutectic or eutectoid structure. It is only two phases in it. So if you have a supersaturated alpha phase, it precipitates a lamellar package of a new alpha phase, but with a different composition and a new phase. So the reaction goes like this. This is with the initial composition, and this is with the new composition and the beta phase. Now this interface between alpha 0 and alpha, it is just an ordinary grain boundary, but there is a difference in composition between the two sides of the grain boundary. And this reaction was discussed by many authors, and one used incorrectly the theory of eutectoid growth because the pictures look like eutectoids. So the theory was, if not incorrect, it was at least incomplete. Already in a 1968 paper, Mats presented or discussed this process, and he used Gibbs energy diagrams to illustrate various phenomena. For example, discontinuous precipitation. In 1972, Mats develops the first satisfactory, I would say, the first satisfactory theory for discontinuous precipitation. And he illustrates this with the Gibbs energy diagrams, and he emphasizes the importance of coherence stresses in the alpha 0 grain boundary. So here you can see typical Hillert style of Gibbs energy diagrams. So this is, this is introduced to make it simpler to understand what is going on. It was, the great achievement was to stress the importance of the coherence stresses in the grain boundary. Now, suppose that you have a similar situation, but there is no beta phase at all. There is only one phase alpha. Gary Purdy and Mats, they studied addition of zinc to pure iron. And then they found that a grain boundary could move even in a one-phase material where when you add zinc or add an alloying element. So here is a micrographs, and here is initial pure iron, and these regions where the grain boundary is here now, and this region which are left behind the grain boundary, they have a high zinc content. And they call this new phenomenon chemically induced grain boundary migration, but later the term diffusion-induced grain boundary migration became generally accepted. So one can notice here that DIGM leads to a mixing at low temperatures where volume diffusion is too slow to allow mixing. So DIGM makes use of the high diffusivity in the grain boundary and the relatively high grain boundary mobility. So this grain boundary leaves a region with higher zinc content behind. Well, there is a driving force for the process. But this driving force was really controversial. So Mats and Gary Purdy, they thought it was a chemical driving force. But if it was a chemical driving force, then in an ideal solution, it would be possible to see DIGM. And that is counterintuitive. It just comes from the entropy of mixing. And I remember Mats said once to me that nothing good comes from entropy. Okay, so then he discussed this issue more, and he concludes that if the lattice parameter of this phase to the grain boundary. And those can actually be a driving force for moving the boundary. And that means that if there is a system where the dependence on the lattice parameter with composition is not so strong, you would not see DIGM. And this has to some extent been confirmed experimentally by other authors. Martensitic transformation, it occurs by a coordinated motion of dislocations leading to the migration of an essentially coherent interface. And it is then much faster than the massive reaction which we discussed earlier. Already in 1958, Mats discussed the thermodynamic aspects of a martensitic transformation. And he derived expressions for the critical temperatures, assuming that the transformation was adiabatic. Now, that cannot be the whole truth. So Mats later realized that there must be a barrier for the martensitic transformation. And Mats, 1997, and Annika Borgenstam, they analyzed experimental information on the martensite start temperature in a number of different binary ion-based alloy systems. And then they could use thermodynamic databases to evaluate the driving force as a difference in Gibbs energy between austenite and ferrite for the composition and temperature reported. And this driving force would then be used to overcome a barrier. And at that time, they concluded that this barrier only depends on temperature and not on alloy composition. So here is a diagram from the report. Here is temperature, and here is the driving force. And those are curves, solid curves for a large number of systems. But of course, there is some experimental scattering. So they concluded that this dashed line would be the barrier as a function of temperature for lath martensite. And for plate martensite, they suggested a constant value. Okay, thermodynamics. Now this picture shows Mats together with Timo Ansara and Gerhard Linden at the CALPHAD meeting 1978. And as you can see, they are not only, well, they're actually working with all their papers. So Mats explained his vision in a ASM Seminar 1968. He wanted to develop thermodynamics into useful engineering tool in metallurgy. And he says, the main purpose of this paper is to emphasize that the situation can now be changed, thanks to the development of the computer technique. The metallurgists should now stop doing what the computers can do. The metallurgists should concern themselves with applying the thermodynamic principles to phase equilibria, but they should rely on computers in carrying out the mathematics. And here is a diagram in a ternary system, ternary Gibbs energy curves in the same paper. And in a later paper, he presented a general method to calculate phase equilibria in complex systems. And this is described in more detail in a later paper in 1981. And this is a method which was implemented by Bo Jansson in the first version of Thermocalc. In the 68 paper, it is clear that models are needed to represent the thermodynamic properties of phases. Until then, Mats had used ideal solutions or possibly regular solutions. And he did not pay much attention to the data you needed in the models. And then he was inspired by the work on ionic liquids, by fluid, and by Blander. So he and his colleague, Lars-Ingvar Staffansson, they started to develop a regular solution model which would cover those earlier models. And it was based on two sublattices, and it was published 1970. So they consider a formula unit like this with A and B on the first sublattice, C and D on the second. And A and B would then, for example, be cations, and C and D anions. Now, if you replace D with vacancies, you look at this formula unit and take A and B as substitutional, excuse me, and C as interstitial solute. Then you can use this as a model for an interstitial solution of this type. Now there are four constituents in the model, and you may think that this is now a quaternary system, but it is actually a ternary system because those four components, those four compounds are related by the so-called reciprocal reaction. You can plot the concentration in this square. So here you add B and here you add D. And here is a Gibbs energy diagram with a Gibbs energy of the four different compounds. And this distance here represent the Gibbs energy change of the reciprocal reaction. At low temperatures, when the entropy is not important, you can see that this model would lead to a miscibility gap. So all reciprocal systems have a tendency to form miscibility gaps at low temperatures. 1981, Bo Sundman and John Ogren extended the model to cover any number of components and sublattices. And this model was later called the compound energy formalism. And in a paper 1986, Mats and co-workers demonstrated the application of the model for ordering phenomena and complex intermetallics. And then they also formulated the model to include, to cover melts, where you could have a different tendency for ionization. So going from a metallic liquid to an ionic liquid. And this model was applied by Mats and co-workers, particularly Malin Selleby, to many oxide and molten slag systems. But it could also be used to treat defect chemistry, where the Kröger-Fink notation is traditionally used. And Mats showed that by using the compound energy formalism, you could treat these defects in a much more general way. And this is a diagram from a paper by Xing Chen and Mats where they applied the formalism to semiconductors, and this was for germanium arsenide. The magnetic effect. Magnus Jarl and Mats, they developed a model for the magnetic contribution to the Gibbs energy of pure ion. And that was based on an expression for the magnetic part of the heat capacity, which had been suggested by Gerhard Linden a couple of years earlier, which made it possible to account for the magnetism in thermodynamic calculations. But it was not until 1982, Bo Sundman and Staffan Hertzman turned this model into a more convenient form. And it has many shortcomings, but despite the shortcomings, it allowed a systematic description of the magnetic alloying effects and is used worldwide. International leadership. Well, here we have some early CALPHADians, probably early 80s, and you can recognize here Mats, of course, and this is Peter Miodownik, Tim Chart, and here is Bosse Sundman, and Malcolm Brand, and Imo Ansara, Claude Bernard, Klaus Hack, I believe, and Bo Jansson, and Alan Dinsdale, and Leo Lucas, and some other persons. And I can recommend this paper from Spencer, a recent paper, and it describes the early CALPHAD, CALPHAD activities, not CAPLAD. When Mats started with the thermodynamic calculations, he realized that this was a tremendous task, and no one could do this by themselves. One had to have a collaboration. And 1970, Larry Kaufman and Imo Ansara, they sent out a letter to researchers they thought could join a collaboration. And they wrote, "We believe that substantial progress can be made in a short period of time if we could arrange to work together for 1 week at one of our facilities to define problems, disband, carry out some individual activities, and meet again for a week at the second facility to compare results and chart future activities." So at that time, there were only 3 groups in Europe that performed thermodynamic calculation of phase diagrams. There was in Grenoble, Imo Ansara, in Stockholm, Mats Hillert, and in Teddington, at that time it was led by Oswald Kobachevsky. So the first meeting was in 1973. It was organized by and hosted by Larry Kaufman in Boston. So there were 13 scientists from US and Europe attending the meeting. And in particular, of course, Ima Ansara, Philip Spencer, Mats Hillert, and John Kahn. And this became the annual CALPHAD meeting. And in a very intensive collaboration between the conferences, which was in agreement with the initial idea. And Larry and Mats took the informal leadership in this development. STT, Scientific Group Thermodynamics Europe. Well, the initial aim was to compile a database for all inorganic substances. And it was initially financed by the European Economic Community. KTH became a member in 1977, although Sweden was not at that time a member of EEC. But one needed the activities of so much, so there was an exception. And early activities, they involved standards, discussing and adopting standards for models, for data, and for reference data. And Mats was the informal leading person here, I would say. The book. Well, the book is really something. It summarizes so well Mats' deep insights in thermodynamics. It's a book that you need to read carefully because every sentence contains a lot of information. And here is typically what it could look like. And then the Mats, together with Malin, developed a lot of educational material, which I believe is available for downloading. And I think I'll stop with this very nice picture of Malin and Mats, just a couple of years old. Thank you very much.